Well, welcome back, everybody, to the afternoon session of the Tine Haworth Cardiovascular Research Day. It's a real pleasure to moderate this next session, which is a new format for the Libin Research Day this year. And what we're going to do is something called TED-style talks. So I'm not sure how many of you are familiar with these talks. They're called TED, and it's not because they're named after someone called Edward. They actually stand for something. So they stand for technology, entertainment, and design. And these are a little bit different than the typical scientific talks we're used to giving. Generally, they are given by influential speakers who are identified with ideas worth spreading. And the format is designed to be entertaining and engaging and make research and science accessible to everybody in the audience. And so that's the goal that's been put forward to 5 speakers that were nominated this year to be the inaugural speakers for our TED-like talks. And they've been very brave to do this year, so thank you for agreeing to do this. They all represent various aspects of research that happens within the Libin Institute, and they really represent the face of the future researchers of our institute. So it's a real pleasure to have them all here today to speak to you. They've been given a tough task to distill their research down into 8 minutes, so they have a little bit longer than the rapid-fire trainees did this morning, but still, we've asked them to present it in a way that takes us often out of our comfort zone a little bit in how we present. So we're going to get started, and I should just say that apparently it costs a little bit of money to get the licensing for TED Talks. We weren't able to do that this year, so we can't actually use the official TED name. So we've had to change it to TOD Talks. But it's not for Todd Anderson, because actually we've decided it's going to stand for Training, Outcomes, and Determinants. And so these will be the first TOD Talks this year. So our first speaker is Christopher Sarsens. He's a PhD candidate in biomedical engineering, and his mentor is Christina Rinker. And Christopher is going to talk about a new paradigm in vascular drug delivery, understanding nanoparticle association with endothelial cells under flow. Chris, thank you.
Hello, everyone. Today, I want to talk to you about nanotechnology. Now, the basic idea behind nanotechnology is that the basic idea behind nanotechnology is that we can use the special properties that materials have at the nanoscale to accomplish things that we wouldn't otherwise be able to accomplish. So nanotechnology, in the not-so-distant future, will enable us to create batteries which can last for weeks but charge in just seconds. It will also allow us to create cars, buildings, and even clothes which never need to be washed because they just don't get dirty. Now, when we start using the basic principles of nanotechnology to solve problems in human health and disease, then we enter a field known as nanomedicine. Now, when you think about it, all of the basic functionality of our bodies, all of the basic machinery of our cells is at the nanoscale. So when we talk about proteins, enzymes, nucleic acids, all of these things are on the nanoscale and function at the nanoscale. So to put it in other words, Mother Nature operates at the nanoscale. And if we want to beat Mother Nature, we too have to operate at the nanoscale. So what does this look like? What does this mean working at the nanoscale? Well, if you read a bunch of science media, you see pictures that look something like this. Now here we have nanoscale robots, which are designed to patrol the bloodstream and to attack disease the moment it arises. This is a little bit unrealistic, and frankly, it might be impossible. But that doesn't mean nanotechnology is a pipe dream or that it doesn't exist. It just looks a little different. So when we talk about nanomedicine in terms of today's technology, what we're really talking about is nanoparticles. Nanoparticles are just very small pieces of matter. They're just particles that are on the nanoscale. And when we talk about nanoparticles used in medicine, they look a little something like this. So here in blue, you can see the core of the particle, or the nanoparticle itself, and then it has this red and white coating on top of it. The purpose of this red and white coating is to modify the interactions between your body and the particle. So essentially, you can think of these particles as very tiny capsules. And when we think about them this way, we get into another concept, the concept of nanocarriers. So now we have a payload, for instance, a drug, and we have a surface coating which changes the way it interacts with your body. So it can protect your body from the drug and protect the drug from your body. And this gets us to probably the most important concept in nanomedicine, which is targeted nanoparticle drug delivery. The idea here is that conventional medicines are, when injected into the body, distribute themselves relatively uniformly throughout your body. Now that's a bit of a simplification, as you probably well know, but for the purpose of this talk, it's close enough. Targeted nanomedicines, on the other hand, can greatly increase the dosage at the local target site and reduce the dosage in the rest of your body. So these particles have the potential to simultaneously improve efficacy of your drugs and reduce potential side effects. So I'm sure you can imagine how that could be a very important breakthrough. You're probably wondering at this point, where are my nanoparticle drug delivery systems? Where are my magic cures? Well, as it turns out, for this, like many things in life, and just about everything in science, it's easier said than done. One of the issues that we found for this kind of technology is what I like to call transport obstacles. So when you think about the path a nanoparticle has to take from the site of injection to the site of action, there are a number of obstacles that have to be overcome for it to get there and get there intact. Here's an example of one of those obstacles. This is extracellular matrix protein, specifically collagen. Now, it turns out that collagen is a major impediment for nanoparticles used as drug delivery systems. The issue with that is that collagen is found throughout your body, so it can pose a major obstacle. Now, this is an electron microscope image of collagen, and this gives you an idea of what it looks like from the particle's perspective on a very small scale. So, putting it on more human terms, you can think of the particles moving through these gels as you trying to escape from a forest that looks like this. You can imagine that while you probably would be able to escape from this forest, it's not going to be easy, and it's certainly not going to be quick. And that's what I study in my research. I look at how nanoparticles move through extracellular matrix and extracellular matrix gels. And we found a few things in our research. The first thing we found was that the density of the collagen matters. So you can imagine that if this forest had a few less trees in it, it'd be a little bit easier to get through. Size of the particles is also important. So if you picture a small child of 9 or 10 trying to escape from this forest, they probably have an easier time than a big guy like me. Furthermore, what we found is that the coating on the particle's surface impacts its ability to move through these gels. So going back to my forest analogy, you can imagine that these two people would have a very different experience escaping from that forest. So we've been able to find out what influences the way particles move through these gels, and we were able to come up with a suite of particles which can be tuned in terms of their transport through these gels. Now, not only does this allow us to design particles which can move better through these obstacles and better overcome these obstacles, but knowing this information, we can actually turn it around and turn an obstacle into something that's to our advantage. Let me give you an example. This is a histological image of an atherosclerotic plaque. Now, as I'm sure many of you are aware, atherosclerotic plaques often consist of a lipid-rich core with a fibrous cap on top. Turns out that this fibrous cap is extremely important for predicting patient outcomes because you can get thrombosis and even death if those plaques were to rupture. So understanding when these plaques will rupture and what determines their rupture risk is extremely important. And since we know that fibrous caps, their strength of fibrous caps depends on the collagen content to a certain extent, and we know how these particles move through collagen gels, then by administering particles to a patient and looking at how they distribute themselves within these caps, we can predict collagen content and even rupture risk. So now, not only can we get an idea of the size and the geometry of the caps, but even their molecular makeup. Let's talk about another obstacle. These are endothelial cells. Endothelial cells line the interior of your entire bloodstream. They line all of your blood vessels. And it turns out they like to take up nanoparticles. Now, if endothelial cells, because they're so numerous, are taking up a lot of these nanoparticles, then there's not going to be a lot left to get to their target site. So this can be a major obstacle for nanoparticles. But again, by further studying the problem, we've come to understand that these particles tend to accumulate in endothelial cells that are exposed to lower shear stress as opposed to those that are exposed to higher shear stress. So in high flow blood vessels, we find that we get less accumulation of these particles than in lower flow blood vessels. And we can even go one step further and say that we find that there's higher accumulation of particles, here seen in blue, in the lower shear stress regions of a single vessel than in the higher shear stress regions. Now, how can we take this knowledge about an obstacle and again, turn it around to our advantage? Well, one important pathophysiology is that tumor vessels are known to have a very disorganized and immature structure because of rapid angiogenesis. And we know that the flow inside these disorganized vessels is typically lower and weaker than the flow inside normal vasculature. So by encapsulating anti-angiogenic drugs into nanoparticles, we can actually get selective delivery to tumor vessels and administer the anti-angiogenic drugs only where they're needed. Nanotechnology is going to revolutionize our lives. It's going to change the way we view technology and the way we see the future. And that includes nanomedicine. Things like nanoparticles and nanocarriers will become ever more present and ever more important, along with a whole host of other nanoprefixes in development to bring real change, real progress, the nanorevolution. Thank you.
Great job. Great job, Tris. That's very interesting. So we're going to take it open for questions here. If there's any questions in the audience about nanotechnology for Chris. While we're waiting, I'll start with one. How far away are these from actually entering the world of human trials?
So nanotechnology in simple forms already exists. So the first nanoparticle drug delivery system for delivering doxorubicin to tumors was approved in 1994, I believe. So there are more of these that are approved every day and more of these in development every day.
Yeah. Can you outline, thank you for your speech. Can you outline what way the endothelial cells are taking these up? Is it endocytosis? Is it a targeting antibody?
So the particular particles which were used in that image are what are known as non-targeted or passively targeted particles. So they have no active ligand receptor targeting. So those would be taken up by likely primarily endocytosis, but there's also a few other mechanisms that are possible.
Hi, really interesting research. I know that, as you say, they're using it in cancer tumors. Are there other areas that they are now working on a little more?
Yeah, absolutely. So the early research in nanoparticle drug delivery focused on tumors, and there's some very good reasons for that, including the leakiness of tumor vasculature, which allows accumulation. But tumor vasculature is not the only angiogenic pathophysiology. So we can look at things like atherosclerotic plaques, which also have angiogenesis and are characterized by angiogenesis. So there is potential for delivery there, and there's lots of particles in the works for that. So there are also more generic particles, for instance, iron oxide contrast agents that are nanoparticles, which are used for a range of different applications. But primarily the ones on the market today, to the best of my knowledge, are for tumor applications, but the research is for really any disease you can think of that would benefit from selective targeting. There may well be. I saw a presentation a couple years ago now on nanoparticles which present antigens, and they modulate the immune system, and they actually can dramatically improve the symptoms for diabetes and things like that.
So one last question is all we have time for.
Thank you very much for introducing this fascinating technology. You said before that there is more like a passive agglomeration in endothelial cells. Cyclodextrins, for instance, or other nanoparticles for drug delivery would use also probably receptor-associated kind of like uptake. Do you have any kind of expertise where this is leading in the future? Is it the same way? Is it a different mechanism than the one depending on shear stress?
So if I understand your question correctly, you're asking me the future for actively targeted particles, for ligand receptor specifically targeted?
The difference, predominantly where it could lead to.
So active targeted particles are a very exciting field, and there's a lot of research into how those particles interact with cells, how they're taken up by cells, and how they can improve delivery to cells. The issue with active targeting is that it requires you to get extremely close. You have to have your ligand bound to the surface of your particle, able to interact with your receptor on the surface of the cell. So we're talking about nanometers apart, right, or even less. So those kind of scales are pretty difficult to achieve. So while there's a lot of very promising research early on to try and get the particles to go into cells, they haven't moved past in vitro, really, because of the fact that you have to get them to that close proximity with the cell. So you have to get them through extracellular matrix, outside the blood vessels, all of these other transport barriers. But there's no doubt that active targeting particles will be a crucial part of this nanoparticle drug delivery systems, because they are taken up in so vastly greater numbers.
I think we're going to have to put Chris out front to field questions over the break, because obviously you've piqued everybody's curiosity with this. So thanks again, Chris. A wonderful presentation. So our next speaker is Dr. Min Jun, who's going to hook himself up with the microphone here. Min is a postdoctoral fellow in the Division of Nephrology Research Group. He is mentored by Dr. Brenda Hemmelgarn, and Min is going to speak to us today about beyond the world of randomized controlled trials.
I'll let that sink in for a couple seconds. So if you've seen the Matrix movies, this man standing behind me is going to be pretty familiar to you. This is Morpheus offering Neo, who's the main protagonist of the movies, a choice between the blue pill and the red pill. Now, without going into too much detail, as I don't want to ruin it for people who haven't seen the movies, perhaps I will anyway. What Neo does, without perhaps rushing into a particular decision at this point, is that he rushes for the red pill. And backtracking a little bit, if Neo takes the blue pill, his life as he knows it continues on. But if he chooses the red pill, he gets to stay in Wonderland and find out a bit more about the Matrix. So he does go on and chooses the red pill, and the movie unfolds from then on. Now I want you to imagine this to be a clinical setting. Dr. Morpheus here offers a choice to Neo, who is the patient, say, for example, has chronic back pain. Perhaps this time around, Neo should take a moment and pause and figure out some of the questions or issues that he should potentially discuss with Dr. Morpheus here before he jumps into a decision about a treatment option. And these are some of the questions that he could potentially consider. Now, I don't mean for you to read all of those individually, but the point is that there is a process or even a list of considerations that a patient should consider along with their doctors before jumping into a decision about making a treatment option. And one of those important factors is at the top of the list, safety. And indeed, achieving this balance between safety and efficacy is something that many clinicians grapple with in the clinical setting. So the next question is then, with so much information out there, where do you source your reliable information from? What do you base your decision on? The hierarchy of evidence tells us at the top of the pyramid is our randomized controlled trials, or systematic reviews of randomized controlled trials. And indeed, randomized trials have been tremendously informative in terms of informing us of the efficacy of interventions going back to, all the way back to the 1940s to the very first one. And I don't need to emphasize to a cardiovascular research audience the amazing or great advances that we've made over the last few decades in terms of cardiovascular medicine and disease. So then, without a doubt, randomized trials are indeed the gold standard when it comes to assessing efficacy of interventions. But is that the whole story? While they do have the reputation of being the gold standard when it comes to determining efficacies of interventions, they're certainly not without limitations. I don't mean to offend any trialists in the audience, but I'll take you some of the potential limitations of trials. First of all, they're very expensive to run. They can often cost millions of dollars to run or perform randomized trials. In some instances or contexts, it might be impossible or indeed inappropriate to run a randomized trial. Often trials aren't long enough and they fail to pick up certain safety events, particularly if they're rare or take a long time to develop. And perhaps most importantly, trial data has oftentimes limited generalizability outside the population that it was originally tested in. So for example, behind me is a list of the inclusion and the exclusion criteria of a typical trial. Again, I don't mean for you to read those individually, but the point is there are almost 5 times as many reasons to exclude a patient as opposed to reasons for including them. So then what happens is that people who go into a randomized trial often don't necessarily represent the broader population in which they were originally sampled from. So what are we missing here? What's the missing piece? I mean, how do we assess the effectiveness of an intervention? How do we address some of the limitations of randomized controlled trials? And the answer is large population-wide observational studies. And these study types have a number of advantages. First of all, they can include a vast number of participants with a very broad-ranging characteristics. They're relatively, compared to trials, fast to perform, quickly, they run quickly, cheaply, and also can pick up safety events which may not necessarily be picked up in a trial setting. So data linkage is now widely used as part of these study types. And indeed, within our own research group, this is what we use. And this is a schematic of our data sources in the Alberta Kidney Disease Network and the ICDC. Here we obtain different pieces of information from disparate or different sources of data by linking all of these data sources into one using a patient identifier number. We obtain information from the population registry, prescription drug information from Alberta Blue Cross, hospitalizations from inpatient encounters, and also laboratory data which is obtained from across the province. And so this ability to link data allows us to perform a range of different real-world-based studies, including this one here, which assess the association between high-potency statins and rates of admission for acute kidney injury. The study itself really shows you of how powerful this type of study could be. And without going into the results themselves, I'll point some of the important factors behind this study. The study included over 2 million people across 7 different Canadian provinces, spanning actually a greater than a decade of study follow-up period, things which would simply be infeasible in a trial setting. In addition to those factors, randomized trials are important in hypothesis generating. That is, they help formulate an idea or a new hypothesis that can be tested in a randomized controlled trial setting. For example, warfarin, which is a blood thinner, is highly effective in reducing the risk of stroke in patients with atrial fibrillation, so much that the magnitude of benefit reaches up to 60%. So the risk-benefit ratio of warfarin is pretty much straightforward in the broader atrial fibrillation population, where the stroke benefit outweighs the risk of major bleeding. But among patients with kidney disease, the story is not so straightforward. Patients with kidney disease have reduced kidney function and already are at an elevated risk of bleeds, throwing off that risk-benefit ratio. So what we want to do is test whether indeed patients with reduced kidney function and atrial fibrillation receiving warfarin experienced increased rates of bleeds. And it appears that they do. The results behind me show that over worsening levels of kidney function on the y-axis from good to poor, on the x-axis are the rates of major bleeding. You can see that with progressively worsening kidney function, patients experience increased rates of major bleeding. And this is particularly apparent in the first 30 days of warfarin therapy, suggesting that among patients with reduced kidney function, it seems as though we need a randomized trial to test whether the same risk-benefit ratio applies in patients with reduced kidney function as it does with a broader atrial fibrillation population. Although, despite all the factors that I've mentioned in terms of advantages, observational studies are certainly not without limitations themselves. And we do need to be cognizant and we need to be aware of these factors, as highlighted by this article that was published in the BMJ, that suggests that observational studies should carry a health warning. So then, what do we need to do? How do we best take advantage of both the world of randomized trials and observational studies? The first is that we need to acknowledge that while trials certainly can't replace randomized trials, they do have a certain capacity to address at least some of the limitations of randomized trials. Secondly, we also need to acknowledge that observational studies themselves have certain limitations and indeed are prone to a range of biases that we need to be aware of and address appropriately using appropriate methodologies. So I know the idea is to try and avoid as much text as possible in these types of talks, but I thought this quote summarized the point I'm trying to get across beautifully. So it was published in the New England. It says, "To understand everything we should know about a drug, we must do both kinds of research with rigor and humility. And if we do that, perhaps we can achieve some level of peace between the trialist and the pharmacoepidemiologist." Thank you.
Excellent, Min. Thank you very much. So we'll open this up for questions. While we're waiting for questions, Min, I'll ask you, where does the role of pragmatic randomized trials and registry trials fit in with this topic?
So it really seems to be the direction that people are going towards now, beyond randomized trials. So where a certain intervention is tested in a traditional trial and then gets tested again in what's called a quote-unquote effectiveness trial to see whether it actually, you see the same benefit in the community, say, for example. I think it's still a growing area. There are, for example, registry randomized trials where we try and maximize the use of all the information that's collected, but there are issues with privacy, whether we need to get individual consent from all of the patients that are included in the registry. So I think it's a growing field, but it's also at the same time an exciting field.
All right, thank you very much, Min. That was great. So our next speaker is Kyle Kelp. He is a PhD student in the Department of Community Health Sciences, and his mentor is Dr. Huda Kwan. Kyle comes to us from Alberta Health Services, and he's going to speak to us about using patient experience surveys and linked data to drive healthcare quality improvements.
Great. Thank you very much for the opportunity to speak here today. I really appreciate the experience. In our lives, we are shaped by our experiences. We experience good things, such as the birth of a child, graduation from university. Unfortunately, they don't come without the bad experiences, the death of a loved one, or in my case, the rejection of an abstract. So in large part, we are shaped by our experiences, but our experiences can be also shaped by how we interpret them, by where we are in lives and, our position. I can think of two very vivid experiences in my own life that I'd like to share with you. I grew up in a suburb of Montreal. In the first few days of 1998, as many of you may remember, a very crippling ice storm hit the eastern Canada and northeastern United States areas. Over 3 days, Montreal received over 2 inches of freezing rain, and the damage was widespread. As you can see, the electricity grid was completely obliterated. Things like ATMs, gas pumps, you name it, were rendered completely useless. From a personal standpoint, I must have turned on over 1,000 light switches that week with nothing actually happening. My parents were very consumed with, the fears and the worries that entailed. My mom was on the phone and, frantically with Hydro-Quebec, wanting to know when the power was coming back on. Meanwhile, my dad was nervously pacing up and down the house, worried that our pipes would freeze and burst. So as a teenager with no school in my position, I did what any child would do, well, 18-year-old in my case would do. I got together with my best friend who happened to have a generator, and by day we cleared the streets of debris with chainsaws and helped out our fellow neighbors. And then by night we played video games and drank copious amounts of beer. It was actually a wonderful experience. Fast forward to a completely different experience in my life with a little bit of a different contrast. June 20th, 2013, which actually happened to be my wedding anniversary. About 6 months prior, my wife, my young son, and we moved to Alberta so I could work for Alberta Health Services. I was on my way into work that morning, and an Alberta emergency alert came over the radio with a report of widespread flooding in Canmore and Kananaskis. I thought, wow, terrible day to be in the mountains, but unfortunately, I was going to work, or so I thought. By 9 a.m., I was on my way home, which was unfortunately my in-laws' residence in High River, Alberta. This picture was actually taken just up the street, and as you can understand, that rest of the day was quite frantic for me and my family. We were basically spent moving things from the basement up to the main floor in preparation for the inevitability that was coming, sandbagging our home and our neighbor's property. Around 4 p.m., we got a pound on the door from the RCMP, basically saying that if we didn't get out, this was our last chance, and they're not coming back for us. So we chose to heed their advice, load 2 suitcases, my son, my wife, and myself, and a playpen into our car, and we stayed overnight at our friend's place in Okotoks. We thought we'd be out for a night. 8 days later, we returned to this. Widespread destruction. We were among the first residents allowed back into High River under the coordination of the Alberta government, the Red Cross, and the Canadian Army. On the left here, speaking of experience, this was my 1-year-old at the time. You could see he was having a wonderful time. On the right is actually a pile of most of our worldly possessions that were now stacked in the driveway, completely decimated. We're truly fortunate over the next 6 weeks when we were truly homeless that we were allowed to stay with family, friends, and we're very grateful for the help we received from our friends, family, and professional colleagues in getting back on our feet. So you're probably thinking, customer service, it's the lifeblood of any organization. Whether you stay at a hotel and the room is dirty, the front desk staff wants to know. Likewise, whenever I do any business with my bank, whether it's opening an account, taking out a loan, you name it, I could expect a phone call in the days that follow to hear about the service and the experience that I received. It may seem trivial to all of us, but this is it's a wealth of information for these organizations who are seeking to improve their services. So you may be thinking, why is this handsome PhD student talking about customer service? What does this have to do with healthcare? And I can never keep a straight face when I say that as well. So I'd actually argue the two go very much hand in hand. As Canadians, we're very proud of our healthcare system. It's one of the things that define us. The other aspect about it is that we have universal coverage by way of the taxes that we pay. So in a sense, we are customers because we pay our taxes, hopefully. So as a full-fledged paying member in this healthcare system, you may be wondering, how can I provide my feedback? Or perhaps more importantly, how is my hospital doing? In 2002, the Canadian Health Services Research Foundation released a paper which aptly said, patients in Canada can look up safety ratings on hedge trimmers and minivans, but why not cardiac surgery? You may be pleased to know that in Alberta, if you're hospitalized overnight, you may have the opportunity to fill out a survey about the care that you received. The survey is administered at 93 sites across the province and encompasses things like care from doctors, care from nurses, medications, discharge information, and patient-centered care. In all, about 20,000 surveys are captured each year. This patient experience data set is the cornerstone of my PhD work. Here I've shown the Institute for Healthcare Improvement's Triple Aim framework. I know many of you are familiar, but it's a framework designed to optimize health system performance. My research focuses on that lower left corner, improving the patient experience. In this aspect, I was able to publish 2 notable papers last year. In the first, I was able to show that in Alberta, it tends to be younger males with higher education who have more dissatisfaction with their hospital care. So in a sense, I am part of the problem. Secondly, I looked at the correlation of all of the items on the survey. There are over 50 questions in total, and the correlation between those individual questions and a patient's overall rating of the care that they receive while in an Alberta hospital. The things that had the strongest signal were care from nurses and coordination of care. So in aspect, it's about the people in Alberta who provide the care and not so much the processes that are meaningful. This is all fine and good, but I feel that the greatest potential for this data is through data linkage. As we heard in the talk before, there's tremendous potential for this. One of the great things about being in Alberta is that we have one system for the entire province. With that, it also affords us several benefits. We can track healthcare use at several touch points in the system, be it a medication prescription, lab test, visit with your family doctor, inpatient hospitalization. From Lac La Biche to Lethbridge, from Jasper to Calgary, it is tracked in a systematic fashion. This linkage of data sets offers the opportunity to answer many, many valuable questions. So about healthcare utilization, healthcare cost, etc. This is widely done in other jurisdictions such as the United States and the United Kingdom, but unfortunately to date Canada has failed to realize this potential. I feel that this is a great tragedy since we already have the data, it's already routinely captured. All that we need are 2 things, a great deal of curiosity and lots of data linkage experience. One of the things that I've looked at, just cursorily, is looking at the percent of readmissions versus responses to this patient experience survey. On the slide that's shown here is one of the questions on the survey relating to coordination of care. Patients who responded that they had poor coordination of care while in Alberta hospitals were readmitted over the next 30 days at a rate of about 10%, as you can see along that y-axis. Patients who responded that they had excellent coordination of care were readmitted at half that rate, about 5%. So some food for thought right there. Other questions that have come out with some strong signals, which aren't shown here, are around discharge information. Did you receive written instructions about the signs and symptoms to watch out for once you returned home? That same relationship is coming out as well. The third and perhaps most crucial component of my PhD work relies in public reporting of this data. To date, we only report a public fraction of it for our top 14 hospitals. This is in contrast to the United States, where it's actually mandated under the Affordable Care Act. What I've shown here is 2 of the questions from the survey. If you're a member of the public, anyone in the world actually, you can go on a website from the Centers for Medicaid and Medicare Services in the United States and look up the results for your hospitals. And I've chosen some hospitals here in Salt Lake City, so it gives you some food for thought. In this third and final portion of my PhD work, I'm going to conduct focus groups and interviews with patients to find out what the appetite is for public reporting of this data, and if so, in what format and with what frequency. I feel that the data can be a very, very valuable teaching tool for both clinicians and patients alike. It may start to spur some questions that patients may want to ask while in the care of providers. It may also show some disparity between what patients feel they're getting as part of their care and what clinicians feel as well. I thank you very much for your time today. and sharing this experience with me.
Great, Kyle. Fascinating stuff. We'll open it up for questions.
Kyle, nice presentation. Can you comment on the rate of response for satisfaction surveys of people who are in the hospital, and how you sort of look at the biases of those people that respond? You know, either they're very happy with care or not very happy with care, and how do you look at that overall?
Sure. Thank you very much for the question. Overall in the province, it's usually, the way that the overall rating of care question is graded, it's on a Likert scale from 0 to 10, 10 being the best rating of care, 10 being 0. And in terms of public reporting, we condense the percent of respondents who respond 8, 9, and 10 on the question, and usually that runs just in the low 80s on a provincial basis, so about 80% rating 8, 9, and 10. Some of the disparities there, of course, I've pointed to some demographic components as well. There are some clinical ones as well, perhaps people who have some chronic needs, who are in and out of the hospital a bit more frequently. Perhaps they feel they have some sort of unmet need, which of course impacts their experience. So that's another area that I'm definitely actively looking at. Thank you.
Thank you. That's a very good talk. You noted about coordination of care during your presentation. So my question is, how do you define coordination of care? Is it different from continuity of care or something else? And also, given the administrative data linkage, there is any algorithm to define coordination of care?
Sure. Thank you for the question. At present, the coordination of care, the way that it's framed to the patient, is the coordination that occurs in between all of the healthcare professionals, so the nurses, the doctors, et cetera, all of the healthcare professionals who provide care during that visit. At present, there's no way of capturing perhaps what that means to a patient, but that is something that may come out from the focus groups. One thing I should say, all of the questions, this is the same survey that's actually used in the United States. It underwent extensive cognitive testing and focus group testing prior to release. So it is a validated instrument, of course. And it's actually used by the Agency for Healthcare Research Quality in the United States. Thank you.
Thank you very much, Kyle.
Thank you.
Great. So our next speaker is Dr. Annegret Ulke-Lemay, a senior research associate from Justin McDonald's lab, and Justin is her mentor. And Anna is going to be talking about how we can detect many proteins in one sample without a single antibody.
So I'd like to talk to you about an exciting new method I'm working with, which allows us to detect many proteins, up to 100, in a single sample in about an hour. And no, there's no need for any antibodies. So all of us who work with cardiovascular research to help cardiovascular patients, most of us are working with people or with some sort of model systems. And then we extract, in order to get data on our patients or model system, we are using some biological samples or maybe some biofluids. And all of those, sooner or later, end up in a test tube. And we're asking, what is in this test tube? We want to know about proteins, because proteins is what the activity of the cells are actually doing, or the change of proteins is the outread of the activity. So what kind of protein is in there? How much did it change? The typical way of doing this is to use antibodies. So about a certain proportion of this audience has been doing Western blottings or ELISAs or the newer Luminex to quantify my protein and to detect it. In the case of Western blotting, we are limited to maybe 5 proteins per sample, if you're lucky. In the case of ELISA, it's very few. In the case of Luminex, that number goes maybe up to 20, but that's it. The thing is as well, antibodies, well, they're really only ever so good. These are an example of my very beautiful Western blots throughout the years. So sometimes we see several bands. We have no idea which one of those is my protein of interest. More often than not, we see no bands, or just some plain ugly results. Or most of the time, the antibodies for my protein of interest is just plainly not available. Just it doesn't appear to create an antibody. So now what are we doing now? Well, I have this sample. I really want to research cardiovascular research. I really want to know something about my proteins. So in comes a new method. Since about 2003, there was a flurry of activities in the world of mass spectrometry. there has been improvement in mass spectrometry instrumentation, methodology, and the software. And this led to the development of multiple reaction monitoring mass spectrometry, which was called MIMMS. MIMMS was termed Nature Method of the Year for 2012 for its potential to really revolutionize medicine. So we are applying MIMMS because it can measure so many proteins at the same time. So it can be multiplexed. I can see 100 proteins, up to 100 proteins if I'm lucky, in a single sample, single experiment. There's no need for any antibodies. And importantly, the only information I need to detect this protein is its amino acid sequence. And ever since we got the genome sequence, I know the amino acid sequence of my protein of interest. Importantly as well, this is targeted, so I can pick which protein I would like to detect with this method, and I go ahead, design my method, and look for it. I don't need any other information about this protein, and I certainly do not need an antibody. I can use all kind of biological samples I would like to use. So in my case, I'm using urine. People have been using blood samples, tissue culture samples, and so on. So in order to do MIMMS, one needs this beautiful machine called high-performance liquid chromatography triple quadruple mass spectrometer, one short LC-MSMS. So this is a machine I personally work with, which belongs to Justin McDonald and Ed O'Brien. So the LC-MSMS works as a filter mechanism. It's like a series of sieves. So what I'm doing is when I have my protein of interest, whatever you happen to be working with, I define myself a prototypic peptide. So this peptide is derived from the protein and is unique to this protein. Because I know all of the protein sequences, I can pick a peptide which is unique to my protein of interest. So what I do now is I have my protein soup in my test tube. I digest all of these proteins into peptides, and I feed it all into my mass spec. The first selection step is the hydrophobicity of this peptide. So the HPLC number 1 selects all of my proteins by hydrophobicity. The hydrophobicity of the peptide is known because I know the peptide sequence. So that's my very first selection criteria. Importantly, this hydrophobicity is very reproducible from one run to the next. So the now selected peptides gets fed into the mass spec for second selection criteria based on the mass to the charge of the peptide. Again, the peptide sequence is known for which I can calculate its mass, and I can calculate the charge based on the amino acids in that particular peptide. So the mass spec selects out only those peptides which meet my specific mass to charge ratio, which are pre-select. So that's my second selection criteria. After these two selection criteria, I'm already down to maybe between 20 to 100 peptides. That's a very small number considering I'm starting with a giant soup in the beginning. So now comes my third selection criteria. I take these peptides and I fragment them further into small parts. Conveniently, peptides fragment along their peptide bonds, so I get bits of amino acids. Again, amino acid sequence is known. I know the size of these fragments, and I can pre-program the mass spec to detect these particularly mass to charge of the peptide, of the fragment in this case. So I have 3 selection criteria in a row I'm using to detect the prototypic peptide derived from my protein. So 3 selection steps. If you think back about Western blotting, I have 2 selection steps. I select based on the size of the gel as well as an antibody. In the case of ELISA and Luminex, I have 2 selection criteria, typically 2 antibodies. In the case of MIMMS, I have 3 selection criteria. I have the hydrophobicity, the size of the peptide, and the size of the fragment of this peptide. The other important thing is the mass spec is so fast that I can detect very many of these prototypic peptides in a single second. So I set the entire mass spec to detect 1 prototypic peptide, then I cycle and detect the next one, and I cycle and detect the next one, up to very many at the same time, which is somewhat limited currently on the speed of the mass spectrometer. So I can multiplex it up to, has been reported, 100 proteins from 100 different peptides. Importantly as well, I can increase the sensitivity and the specificity by using more peptides per protein. Proteins are fairly large, they give me 5 or 10 or 20 peptides. I can try to find all of those and now have very high specificity because I can say I want to find all of those peptides. Again, antibodies usually goes to one epitope, and that's it. So now, where does quantification coming in? So now that I have the 3 selection steps, I can find my peptide, but I want to quantify it. So once I know my prototypic peptide, I synthesize the same peptide with a heavy labeled carbon. If you remember, the carbon-13 is 1 atomic mass unit heavier. So now the mass spec can recognize this heavy labeled peptide and distinguish it between my endogenous. So I use this heavy labeled peptide and spike it into my sample as an internal control at a known concentration. Now I run my method, and the mass spec can distinguish between those two, quantify both, and because I know the concentration of one, I get the concentration of the other. And the prototypic peptide stands directly in for the protein it's derived from, so I get an absolute concentration with this method. So something really exciting I am doing, applying MIMMS in cardiovascular research, is we are looking at people with kidney disease. When people have acute kidney injury, they either go on and recover, or they go on and develop chronic kidney disease. And we want to know why. So what we are doing is we have a set of about 20 disease-associated proteins based on our own research and based on literature. We think these proteins are involved in acute kidney injury. However, out of these 20 disease-associated proteins, 2 have an antibody, and that's it, and no other antibodies inside. So now I can program an MIMMS for that and actually quantify exactly these proteins in my sample. Along goes a couple of control proteins because I can run as many peptides as I want. I'm going to throw a couple of controls in, and a couple of biomarkers which have been published to maybe playing a role as well. So the way these goes in as well. So now I have 30 proteins I'm detecting. So I'm collecting the urine from patients with AKI and detect these 20 proteins, quantify them, and then I can go link back which of those are involved in the development of chronic kidney disease or not. That's really important for biomarker discovery, also as a future drug target. So in summary, MIMMS is here to stay at the University of Calgary. Other than looking for biomarkers in AKI, there's a lot of other things you can do, such as looking for phosphorylation, looking for single nucleotide polymorphisms, or really whatever else you can think of. MIMMS is going to be very important for precision medicine. We're going to hear of that later. And there's still a flurry of activities further improving the field of MIMMS, which will make this field even more important in the future. Thank you.
Thank you for making mass spectroscopy understandable. That's no easy task. So any questions for Anna about this technology?
And I was just wondering, do you think this is a technology that's going to be amenable to, let's say, hospital diagnostics labs and places where this sort of detection and quantification could really help and replace some of the technology that currently exists?
So Andy, I think that's certainly the future. Using this very similar method to detect small molecule is already very, very common in clinical diagnostics. So the method is extremely quick. Between getting a sample and having the data, it's not even maybe a day. And I think the future really is to do that in a clinical setting. It's also fairly cheap. And it's certainly going to replace ELISAs or really compete with those. Yeah.
And one last question here.
How much does the machine cost, and how much does it cost to do a sample?
A sample is between $10 and $20 per sample. It depends a little bit on the preparation. The machine, you'll have to ask my boss. It's not cheap. It's about the value of my house, I would think, plus minus. Plus another. Okay. The value of his house?
House in Vancouver. Thank you very much, Anna. That was fantastic. So our last but not least speaker is Dr. Zardasht Okab, a fourth-year adult cardiology resident. And Zardasht's mentor is Dr. Bob Sheldon. Zardasht is going to talk to us about distinguishing aging from frailty to help us prevent strokes in my neighbor who has atrial fibrillation, the unfrail atrial fibrillation program, and I'm told he wants some chairs on the stage.
Okay, so I'd like to start by introducing you to my neighbor, Frank. He's a pleasant 80-year-old gentleman who's a retired teacher. He has hypertension, diabetes. He's had a TIA 6 months ago, and he's had some mechanical falls in the past and a history of an ulcer. Now, Frank is a very active guy. He's, in fact, his level of activity probably puts some of us cardiology fellows in shame. But he has a dog named Max, and he tends to walk it several kilometers a day, and without any active symptoms. Unfortunately for Frank, recently he's had some misfortunes. He was diagnosed with new atrial fibrillation, and his family physician is unsure what to do with him with regards to his management. Now, atrial fibrillation is the most common cardiac arrhythmia that is prevalent in the elderly. It is associated with a 4-fold increase in the risk of ischemic strokes, and stroke prevention using oral anticoagulants such as vitamin K antagonist warfarin or the non-vitamin K antagonist, the NOACs for short, is the mainstay of management. Now, as good as these drugs are in terms of preventing strokes, they do come with their own side effects of increased bleeding risks. And we don't actually know what to do with the very elderly, as the large phase 3 trials had a small proportion of the very elderly in them. So you can imagine yourself being the primary care physician of Frank and having these difficulties in terms of, do I put him on an anticoagulant or not? And this problem is going to become increasingly prevalent as our population is aging. Which comes to my next point, is that one of the biggest challenges that we're facing in the next decade or even now is of an aging population. In fact, the Statistics Canada predicts that elderly over the age of 65 over the next few decades is set to increase quite dramatically. Compared to 2005, by 2030, by 2030, 1 in 4 elderly will be over the age of 65. Now, this should be a haunting statistics for the clinicians, as our current healthcare system is not equipped to handle the problems of the very elderly. In a recent poll, 1 in 4 Canadians believe that, or think that there's not enough home care or nursing care facilities available for their loved ones who are very elderly. And 1 in 3 actually believe that there's enough hospital beds available to even meet the basic needs of the elderly in the community. And when it comes to why it's important for us in the cardiology world, is that the prevalence of atrial fibrillation increases quite dramatically with aging, with the elderly folks being at highest risk of developing it. And so we have these new drugs, the NOACs. We know how to manage atrial fibrillation, but the biggest problem that arises from it is that the elderly folks are actually not receiving anticoagulants. When we look at across all the studies that have looked at anticoagulating the elderly with AFib, we find that on average about 50% of those who should be on an anticoagulant are receiving anticoagulations with no contraindications to them. And this is a big problem. And so we have to think to ourselves next, then why are only 50% receiving anticoagulation? And could it be due to a misperception on the part of physicians of frailty? So before I go into what frailty actually is, I'm going to ask an audience member to actually come up and help me with the next part of my presentation. And this is going to entail a very demanding, physically grueling test of whether or not to see if you're frail or not. So should I pick, or is someone going to volunteer? How about yourself in the front row? All right. So while my friend here, stretches and warms up, I'll talk to you guys about frailty. So aging. Do we all age the same, or do some of us age more poorly? So aging and frailty are not synonymous. And frailty is defined as a biological syndrome of decreased reserve and resistance to stressors due to an accumulation of multiple defects throughout the years. There are at least two proposed mechanisms, one of which is an increase in the inflammatory cells and a decrease in the androgen production, which leads to a decreased muscle mass. And the second one is an accumulation of defect model of aging, of long-term wear and tear and in the different organ systems, leading to the frailty phenotype, which is characterized by being slow, by being weak, and also just having a lower resistance to the stressors. And so there are over 20 frailty instruments that exist. Some of them require a specialist to actually deliver them, like a geriatrician. Some of them require specialized equipment, such as a dynamometer for grip strength. And they can take from anywhere from 5 minutes to deliver to over 3 hours. So you can imagine yourself in a primary care physician's office that depends on the volume of patients, that may not be the most practical thing. However, there are in existence other more simpler screening tests that we can do, which one of them I will demonstrate now. So Payam here, my volunteer, is going to do what's known as a gait speed test. And you'll see how difficult it actually is. So what I'll do is I'm going to time you, and we're going to test your speed. And that's supposed to be 3 meters, which kind of looks about 3 meters. So you can go ahead and start when you go. And that's it. And that's all it took. Even though he barely made it across, he is not frail. Now, you could imagine yourself, though, that if you were somebody who was elderly, if that distance took you longer than 6 seconds to accomplish, you would be at a higher risk of frailty, and then we would want you to do a more comprehensive frailty assessment. So please give him a round of applause for participating. Thanks, Payam. Now, frailty comes with actual outcomes. So in multiple studies, frailty was found, folks who are frail have been found to have more hospitalizations, worsening disability, being admitted to the nursing homes, having more falls, and even having a mortality, worsening mortality. However, we largely think that frailty is being overestimated in the community because of its subjective measurement of a primary care physician just seeing an elderly folk in front of them and thinking that maybe they're a bit more frail than they are. In a study that was done over 64,000 community-dwelling adults, the prevalence of frailty was found to be only 1 in 4 in patients who are over the age of 85. And that tells you that 3 out of 4 elderly over 85 are not frail. Now let's look at it a different way. So this is a graph that I made myself where I've superimposed in blue the prevalence of frailty, and in red is the inverse of receiving anticoagulation, so no anticoagulation. And what you can see is that there's a large gap that exists between the prevalence of frailty and not receiving anticoagulation. And that's a pretty large gap, and this is the focus of my study, where we actually are trying to narrow this gap. Though there could be many other reasons for why that gap is that large, we think that frailty plays an important role in that gap. And it's also very important because there are currently no guidelines to tell the family physician on what to do about Frank's issue. He doesn't want a disabling stroke, and he's quite afraid of having a disabling stroke because he's still 80, he's very functional, he's got a zest for life, and he's got things that he wants to cross off his bucket list. So for a primary care physician, it becomes very challenging to actually figure out in terms of his atrial fibrillation management. So we have a problem. And we have a paradox in the management of atrial fibrillation. We know that the prevalence of frailty is the highest in the very elderly, but the rates of anticoagulation is the lowest in them. But is it really a problem, or is it a big opportunity for us? And so this is where I'd like to introduce our program, which is called the Unfrail AF program. The Unfrail AF program is headed out of the Libin Institute, and it's a multi-phase study that looks to better understand frailty and atrial fibrillation relationship. The ultimate goal of the project is to answer the question, does objective measurement of frailty using a validated instrument increase the rates of anticoagulation in the elderly? The project is divided into multiple phases. We've already completed a few of the phases that you see up there. We've done a systematic review and meta-analysis of all the literature that exists in the field, which we shrunk it down to 4 studies that actually have looked at this particular issue. So there's a huge paucity of data in this field. We found that the prevalence of atrial fibrillation is 30% to 50% in this 900 or so patients population that we saw. We also found that being frail is associated with not receiving anticoagulation. There's an inverse relationship between frailty and not receiving anticoagulation. Currently, we're working on our next 2 phases simultaneously, where we're studying to see whether family physicians are actually measuring frailty, what instruments are they using, and what knowledge do they derive from those instruments, and how do they actually apply that knowledge to their clinical practice, and whether or not it actually will change their practice, knowing the frailty status of the patient. We're hoping once we're actually able to complete all of these things, we can actually do a randomized control trial to actually be the first in country and even actually in North America or anywhere else to do a prospective study. Because all of these have been retrospective studies, and we would be the first ones to do a randomized control trial looking at it in a prospective sense. I think that this is an important issue for clinicians that are here, or even any care provider that's involved with the care of the very elderly. And I think that we should all become familiar with at least one of the frailty instruments, because the next time you see Frank in your office, you'll know exactly what to do. So thank you, and I'll leave you with that.
Thank you very much, Sardash. That was excellent. So we'll open it up for questions.
You suggested that primary care providers are overestimating frailty, and implicit in that is kind of the assumption that if you are frail, that maybe you shouldn't be anticoagulating. Is there any evidence to suggest that we shouldn't be anticoagulating frail patients with atrial fibrillation?
Yeah.
Why is that a determiner of who should be or who shouldn't be anticoagulating?
Yeah. Thank you for your question. So to answer your first question in terms of the overestimation, there has been a number of studies that have done on surveying the primary care physicians and seeing what factors actually deter them from anticoagulation. And they found things like cognitive impairment, falls, increased risk, increased comorbidities, and these things actually deter them from it. And they have found that when they've looked at it, when they see the patients, it's a subjective assessment, that these tools that we have for frailty assessments are not in clinical practice. So we think that they are being overestimated in terms of a subjective assessment. For your second part of the question, what we're focusing about is not so much to see what happens when you anticoagulate the frail elderly, because we know that the outcomes for the frail elderly are not good. In terms of their outcomes, they have in 6 months, they have 20% or 30% mortality risk. But what we're wanting to focus on is the opposite of that. We want to make sure that the folks who are not frail are not being classified as frail and omitting them from receiving the anticoagulation. So it's a bit of it's different. And I think someone should look at the frail patients whether or not they should get anticoagulated, but that's not the focus of our project.
Thank you, Zardash. So that ends our session, and I'd just like to wrap it up by thanking all 5 of our excellent presenters for taking on this job of presenting this year. You've all did an excellent job with the first ever TOD Talks, and we'll just finish with a round of applause for all of you, and then we can take a break.